Welcome everyone to the 10th anniversary of the Aviation Forum, this year in the digital edition. And I'm more than happy to welcome you to our 3D Experience Aerospace and Defense Virtual Playground. In the year of 2020 and the COVID-19 impact of our industry, it is more than important to look at each other, at collaboration, at the human power to innovate, to thrive successfully throughout the pandemic, but also being competitive and being ready for the next years to come. What we want to share with you in the demonstration are addressed in three different themes of how to build these industry alliances, how to use global collaboration, but also look at how we can still keep the human into the center of making the progress we need throughout our different domains, different projects, driving innovation and driving not only innovation from great ideas, but how to leverage these days to drive innovation throughout engineering, manufacturing, building the aircrafts and systems, and then maintaining it once it comes to life. The playground we want to take you through in the next 40 minutes is really inspired by great projects we are doing with our customers, or we did before, but also doing during the past couple of months and that's what we show in the first chapter, to drive innovation from an idea rapidly into a prototype, rapidly throughout different organizations with teams cross different locations, which is more and more important as we go from lockdown to connect people and work together on a platform to drive the innovation into reality. Second chapter, this is a showcase where we want to take you through a collaboration between an OEM and its supply chain, how to exchange data, how to work together, how to tear down these silos and boundaries between all of us in the aerospace and defense industry and accelerate the projects, accelerate new ideas into the aircrafts, into the systems, or into the production environments. The supply chain is key, but it's also key to understand how can we manage the complexity of our systems. It's growing over time. How do we go from design and influence flexible manufacturing? It's not, as we talked about in the past, only about increasing rate, but now it's how do I manage and build and rebuild my manufacturing system to be more flexible, reacting quickly on market demand changes. And finally, how do we drive excellence and high performance in operations for execution of the production? But also, once the aircrafts and systems are up in the air flying, need to be maintained. How do we address this and push the boundaries of a digital continuity into operations? Introducing to you 7 of our pods we want to take you through on the journey, starting with the acceleration of innovation, with the experience centers we build up around the world, where we take our innovative customers through projects, a combination of digital platform on the 3D experience platform, but also the latest and greatest of the manufacturing industries in terms of robotics, virtualization, and immersive technologies of building this rapidly, but also always keeping in mind the collaboration of people who are involved in this process. And then we go from part 2, starting the collaboration between the OEM and its supply chain, how to share data, how to collaborate, how to be always up to date, how to break down the statement of work, but always working in a lockstep together towards the target. System complexity, when we look at the new innovations which are up on the horizon, electrified aircrafts, new systems in the aircraft, new entertainment system, new systems required to bring back the passenger confidence to fly again in a more safe and secure aircraft cabin. All this adding to the overall complexity of a system in the aircraft and the collaboration needed between the supplier providing the interiors to the OEM. Then we go and look at the digital manufacturing. How can manufacturing influence engineering? How can we influence the next generation of the future factory? What kind of materials, what kind of new machines, how to connect all this together to get it up and running? how to make sure to meet flexible rate at the end. Then we continue to pod number 5. This is called continuous program optimization, and there is really the foundation of the 3D experience platform, the collaboration, sharing ideas, sharing common targets for a program and work against it, leveraging the knowledge of everyone, leveraging the knowledge and content and know-how in the digital environment of the immersive 3D model-based design and manufacturing. Then we go pod number 6 on the execution of manufacturing operations, and it's not on just talking about execution, but also how do we connect to machines, how do we coordinate with machines, how do we schedule with machines, and the constraints we have different sites, different suppliers, how can we all bring this together to what we call manufacturing operations excellence. Again, as we learned from the past months and year almost, that's a key aspect to stay in the market and stay competitive. Last but not least, pod number 7, 360 service operations excellence. This is then pushing it into the MRO domain, into the services of commercial and defense aircraft, how to keep the thread between the engineering, manufacturing into service, and then all the information coming back, the rich information of a life of an aircraft and system, terabytes of data, which captured a lot of knowledge, which needs or should go back to the engineering to drive continuous optimization, drive collaboration, drive new services, new opportunities for you to offer in the market, of keeping fleet availability higher than they are and keeping the cost of maintenance as low as possible. So enjoy going through the 7 pods, and if you got a little bit excited, if you understood the vision we are driving, and it's not only a vision, it's really a strategy. We want to partner with you to help you to get through the crisis, be ready after the crisis, and then staying competitive, innovative with all your employees in the market. Leverage this power you can build, the content know-how, the innovation, to be more flexible for the future, to be more innovative, and to drive and support this industry. So we would be more than happy to get in contact with you afterwards. We are here for you. Please reach out to us, and then we can go together on this journey. Thank you very much. Enjoy the pods.
Hello. Welcome to pod number 1, Accelerating Innovation. What would it mean to you to have access to the right data, the right applications, systems, and processes, and most importantly, to reconnect with the right people at the right time in achieving your mission? Welcome to this brief introduction of the 3D Experience platform and a story that illustrates how the only progress is human. Using a standard web browser, we have access here through the compass in the top left corner of the screen to the roles that are assigned to me, or for any individual in the company, and for all aspects of their business, from engineering to production, as you might know, but also including legal, general and administration, human resources, sales and marketing. For each role, there are a set of applications that are available. Those applications may be from Dassault Systèmes, from third-party software, or developed in-house. To learn more about these roles and applications and how we can support global business and processes in collaboration with your value network, request a meeting with an expert following this introduction. Now that we know how the platform is a critical information and business system, I'd like to share with you an amazing use case accomplished by Airbus team you see in the lower left. This team modeled, as seen in the lower right, and built a fully functional thrust reverser unit. What was remarkable about this engineering sprint is that the project was completed in only 84 days, significantly less than this dispersed team of experts would typically accomplish in their own office. They came together on the 3D Experience platform and in a unique facility called 3D Experience Center, located in Wichita, Kansas. Part of the Wichita State University Innovation Campus, the team also worked with students from the university, as well as with experts from the National Institute for Aviation Research, NAR, to develop new working methods leveraging the various labs available, including the Immersive Technologies Lab, a multi-robotic advanced manufacturing lab, a reverse engineering and inspection lab, and a new materials and 3D printing lab. Extremely pragmatic in approach, these new methods are not idealizations, but can be taken back into your production environment. The 3D Experience Centers are part of a global network we are building with universities, authorities, and industrial partners. As you see here, the Wichita Center is live. Centers in Seattle, Toulouse are work in progress. Various centers are also active in India and across Asia. Contact us to learn more about visiting the Wichita 3D Experience Center and setting up a one-day visit, multi-day, multi-week, or 3-month program. For you in Germany, contact our team in Hamburg. The Dassault Systems Experience Center is part of the ZAL Technology Center. Sven Lammers would be happy to set up a project there with you. To conclude, it's about connecting the right people with the right resources to develop new, more sustainable, and more resilient ways of working as we move forward together. Contact our experts. We look forward to hearing from you. Welcome to pod number 2, centered on OEM supplier collaboration. We start on OEM's side, where the OEM program director, Pete, logs into the platform and is welcomed by his own customized dashboard. Here, he can aggregate information from different sources, like RSS feeds or customer surveys. This particular survey tracks the criteria that the passengers consider important for air travel, and can become a major KPI for the program, like we see on the screen. Speaking of program, here we have an integrated master schedule view with the collaboration tasks for the supplier. Likewise, we have a supplier network community where the OEM shares information in real time with the whole value network, fostering agile collaboration. If we now go into the Supplier Collaboration tab, we see that there is a dedicated project for the OEM supplier collaboration around the design and the manufacturing of the flap. Here, the OEM can define tasks that will be under the supplier's responsibility. By filtering the collaborative tasks by project, he can reveal the tasks that have been defined in the context of said project from an assignee, owner, or reviewer point of view. On any given task, he can assign people from his company or his value network to perform the work. In addition to that, we also have the so-called bookmark spaces in the 3D Experience platform. These bookmark spaces act like secured folders in the database where the OEM reveals information for the supplier so that they can easily retrieve the data and work in a collaborative manner. Now the dashboard has been shared with the supplier. We are now going to the head of supply chain and we see him log into the dashboard. In the Supplier Selection tab, he checks the status of the supply chain and envisions some alternatives or what-if scenarios. By looking at the real-time KPIs and by analyzing the different actors of the supply chain with respect to these different scenarios, he can optimize their behavior. Adding or removing suppliers is possible in order to meet business objectives such as desired production rate, capacity, or quality, for example. Now, on supplier's side, the supplier program manager has now access to the dashboard. He can view the information that the OEM has decided to share with him. In this case, 2 projects have been shared: the overall master program project and the specific collaboration one, centered on the flap. This way, the supplier sees their own tasks, the related data along with the expected deliverables. As you can see, the supplier can review the different tasks that are the responsibility of the OEM and their own. Many tasks have been assigned to the supplier, so he can start working on them right now. The supplier has also access to the bookmark spaces that the OEM has decided to share with them. They can review the data that has been revealed by the OEM. In this case, we can see the space allocation mockups that are going to drive the design of the flap, together with the equipment allocations. The master 3D geometries are also reviewed. It is worth noting that we are checking everything in a web-based dashboard. So all you need is a web browser to access, visualize, and navigate through the data that the OEM is sharing. They are quickly reviewing the wing master geometries to identify the interfaces that are needed for the design. Besides 3D data, the OEM can also share specific requirements for the supplier so that they can take them into account when designing the product. To finish this part of the demonstration, we can take a look at the communities that the OEM has created for the supplier. They can check the information they're in, and they can share it with the rest of the team. Welcome to pod number 3, centered on collaborative multidiscipline engineering. We start on the supplier's side, where the supplier program manager looks at the detailed systems engineering data that the OEM has shared with him. He can take a look at the different requirements set by the OEM for the flap assembly under his responsibility, with full connection to the functional views of it and the logical view beneath it. Here, we can see a traceability view from requirements through functions all the way to the logical breakdown of the flap, showing that each individual requirement shared by the OEM can be traced to the logical component that is supposed to implement it. The supplier can take a closer look at the 3D data coming from the OEM, whether it takes the form of space allocation mockups defining the main equipment volumes for the aircraft, or master geometries. Here, we see another systems engineering view, which places the flap system in the larger scope of the full aircraft, within the full systems architecture. This is what we call an aircraft-level logical breakdown. For the master geometries of the aircraft, the OEM shares the main interfaces that the supplier will need to respect. After checking all of this information, the supplier can start the detailed design. Here we see that, as time progresses, more and more mechanical components designed by the supplier and linked to the OEM's requirements come to life. When design reaches a sufficient maturity, the design review can start. In this case, we can see that there's an easy access to the full engineering bill of materials. In other words, the full engineering definition of the product directly on the web-based dashboard. Besides reviewing only 3D data, inside this web-based environment, the stress analyses performed by the supplier can be accessed. This allows them to check that the design about to be produced actually corresponds to and satisfies the OEM's requirements. We can see the displacements, the von Mises stresses in this static simulation, and for the moment, everything seems to be fine and compliant with the specifications. After completing this internal review, the supplier will be able to signal it to the OEM directly on the 3D Experience platform using collaborative tasks. On OEM's side, the joint design review of the flap assembly is carried out live using the 3D review capabilities enabled by the 3D Experience platform. Again, action and progresses are tracked using collaborative tasks. By leveraging 3D markup, the OEM can directly annotate the 3D data shared by the supplier and use it as a vector of communication. This is model-based collaborative engineering. The design review is carried out without a single document in a web-based dashboard. After performing the collaborative design review, the OEM raises some minor issues, which will be addressed by formal change actions. These issues are tightly connected to the 3D definition of the product and contain all the relevant information for the supplier to treat them. This information can take the form of a product context, a 3D markup with detailed annotations, etc., etc. As we said earlier, the resolution of these issues will be tracked in the 3D Experience platform using a formal change process that includes both the supplier and the OEM. Welcome to pod number 4, centered on supplier design for manufacturing. After the design on supplier's side reaches a sufficient level of maturity, the manufacturing planning can start. The engineering definition of the product, that is, the engineering bill of materials, is restructured and consumed with full traceability and accountability into the manufacturing bill of materials, the MBOM. Consumption is very intuitive, and it can be checked with BI Essentials. This will display a color code telling the user if the products are assigned or not, or if they are even assignable at all. This is what we see here. Some products are assigned directly, and some that are, for example, structuring elements of the EBOM are not. We can now reveal the item update status. It tells us if the MBOM is up to date with respect to any engineering changes on EBOM side. We can also review the process plan for the assembly of a particular part of the flap structure. What we see here is the set of detailed operations and steps inside the process, complete with manufacturing constraints, as well as a Gantt chart of the assembly procedure. This will give us insightful information to estimate the assembly cycle time. Everything that we've done for assembly can also be done for part fabrication. After defining all the intermediary models, from raw material to finished part, we can consume the engineering requirements coming from the OEM or coming from the supplier's own manufacturing engineering department. Each requirement can be assigned to the step of the process where it is relevant. This is paperless model-based engineering. It is what we see here. Once the requirements have been allocated to the MBOM, they can be dispatched to the different steps in the process planning to be used later for the ANSI machine programming. We can also start assigning resources to the different steps that will intervene for the ANSI machining programming. This will complete the programming context, as we will see in the following steps. For now, let's quickly jump to factory flow simulation. After defining the plant layout, we investigate the capabilities of assembly rate using factory flow simulation. It reveals assembly KPIs, buffer zones, cycle times, and allows us to verify that our production planning is on target and that it can satisfy the desired rate expected by the OEM. To finish this part, the manufacturing engineer on supplier side logs into the 3D dashboard and uses a collaborative task to signal that they have delivered both the MBOM and the routings for assembly and for NC machining to the OEM for review. This is done for all of the expected deliverables. After completing this factory layout planning and flow simulation, let's jump back into the NC programming. Here we see that the programming context, which was prepared by the manufacturing engineer, is used by the NC programmer to program the virtual twin of the actual machines that are available on the shop floor and to simulate the material removing process from raw material through semi-finished part all the way to the last finishing operations. Once the programming has been simulated and validated, we can generate the standard machine code and check it before actually attaching it to the routing that will be sent for execution. Here we see that the program is available and we can check it one last time, and then it will be attached to the resources before being sent for execution. One last step is now needed for the full completeness of the manufacturing dossier, which is the work instructions for assembly. So, after finishing the MBOM and the process plans, we document them with intuitive model-based work instructions to make sure that our assembly operators get first-time quality. Welcome to pod number 5, centered on continuous program innovation. We start on OEM's side, where after a major design review, including a major global KPI review, a risk was identified on weight. The program manager takes it upon himself to investigate the weight, to review it, and to then use all the capabilities offered by the 3D Experience platform to assess the weight and review the weight objectives. The weight analyses can begin. After bringing the weight of the flap assembly into the session, he notices that the weight is on target. However, in order to mitigate the risks that have been identified, the target value of the weight for the assembly, under the responsibility of the supplier, needs to be modified. After this modification, the current design of the supplier is over target. The decision to modify the weight and the first actions to address the new weight objective are materialized in a design review, which will result in a change action for the supplier requesting a new part or a new version of the assembly where the weight has been reduced. During the design review, a good candidate for lightweighting using additive manufacturing is identified and shared. Then, the supplier can start working on this issue. Design for additive manufacturing uses the generative design capabilities offered by the 3D Experience platform. The process starts with the creation of a design space around the legacy part, where the main functional regions are defined. The in-operation loads shared by the OEM are applied to set functional regions in order to drive the topology optimization process. A design space validation using those loads is performed. After that, the targets for the optimization procedure are defined. Maximizing the mechanical stiffness of the part while minimizing the weight is the goal here. The functional generative design solution automatically proposes some organic-looking shapes that are perfectly suited for additive manufacturing. The validation of the new part confirms that it performs even better than the legacy machined part. A more in-depth comparison bringing up different KPIs can be done, and all aspects such as weight, mechanical properties, displacement, and maximum stress, and so forth, show that the part optimized for additive manufacturing is superior to the legacy one. Once the design is validated against the in-operation loads, the additive manufacturing process planning can begin. By leveraging digital continuity within the 3D Experience platform, the new part coming straight from design is used to start preparing the additive manufacturing process. The engineer starts by defining an optimized print orientation, either automatically or manually, on a virtual build tray. Then, the optimal nesting and support structures for the part are created, based on geometric and material properties criteria. After that, the slicing and laser scan path, so basically the machine program, are generated, taking into account the real parameters of the actual printer. Finally, some quality analyses and a multi-physics simulation of the virtual print process are performed in order to validate the program. This increases the confidence on the fact that the parts that are going to be printed correspond to the desired specifications and requirements. After validating the virtual print, the legacy part is replaced by its new additive manufacturing version on supplier side. All of the assembly manufacturing planning is updated to take into account this change. The 3D Experience platform automatically highlights the need for design changes integration and quickly enables the user to flow down changes from engineering to manufacturing planning. Now, all of the manufacturing planning for assembly also includes the new additive manufacturing part. Back on OEM side, we can now see that the assembly, after this modification, is well on target, and all the risks for the program have been mitigated. The evolution of the KPI can also be tracked to see that it has been going down consistently until reaching its current value. As always, these activities are tracked using collaborative tasks. Welcome to pod number 6, centered on manufacturing operations excellence. We start on appraisal side, where a production operator called Sylvie logs into her appraisal portal. Because she is responsible for the additive manufacturing facility, she has a real-time monitoring view on the whole machine park under her responsibility. One of the 3D printers seems to be presenting a problem, so she zooms in to investigate. Quite a few defects appear on the machine in their recent history, so the production operator decides to raise an alert for the maintenance department, signaling that there are quality defects in this particular machine. Because she has the responsibility for the whole additive manufacturing area, she goes to check one of the machines that are still running to verify that the production is up to schedule with the desired quality. Here we see that the targets are mostly met with regards to production output and quality is improving. After checking the indicators that she needed, she can take a look at the work order currently being executed on the machine, and she can signal its completion when it is appropriate to do so. Finally, Sylvie, or production operator, digitally validates the production sign-off. If we now go to the production supervisor and scheduler, Claudia, we see that she goes to the aerospace and defense facility and looks at the additive manufacturing area. She realizes that there is a 3D printer that is down and that it is causing some problems, so she will have to take an action. If she goes into her home screen and then into her alert list, she will notice that a maintenance alert created by the production operator Sylvie is present. She decides to take it with a high severity because of the nature of the issue, and she creates a reactive maintenance order, effectively putting the machine offline. In order to keep the production going, Claudia goes to the Ortem scheduling screen and starts changing the planning of the production around the unavailability window of the machine. She does so manually at first, and then she switches to an automatic schedule optimization made by the software in order to improve the planning and secure the production rate. She can compare the different scenarios that she has envisioned in order to choose the best one with respect to specific criteria. For the last part of the video, we're going to see how the 3D Experience platform and Dolmia Aprizo enable quality management for production systems. In this case, we see that one of the serialized units of the manufactured flap assembly is selected, and quality defects are signaled directly on the 3D model of the product. These defects have different severities and different reason codes. Once they are solved, for example in this instance during production, they are closed. As time goes by, and as different defects are signaled on different serialized units of the same product, manufactured items analytics can be performed in order to reveal trends in the global manufacturing operations. Manufactured items analytics connects the dots between production operations and engineering by revealing trends that can result in potential product improvements. We see how the defects are classified according to different categories, such as type and date, and how an intuitive color code reveals the amount of defects per part of the flap assembly. These defects can initiate an investigation procedure, tracked by the means of collaborative tasks, like the one we see on the screen. Here, the head of the quality department is directly assigned on a task with the relevant information to investigate the increase of quality defects reported against a particular part. This procedure may result in a formal engineering change to address the issue. All of the necessary information is directly shared from the 3D Experience platform and contained inside the collaborative task. We can also foster another mode of collaboration involving a broader audience through the 3D Experience platform communities. This is what we're seeing on the screen. Now we can see part of the analysis that is performed on the defects. What we're seeing is a decomposition graph of the different defects for each part with the reason codes, severities, and so on and so forth. This will guide the analysis of the issues. Now we are with the responsible for production quality, who's receiving the different tasks that he acknowledges and starts working on a resolution workflow to address them. Welcome to pod number 7, centered on 360 operations excellence. Let's start by going to the Collaborative Service Cockpit, which is a tab on this 3D dashboard. Here, we have a NetVibes feed reader to gain market insight and awareness. We also have a metrics reader that shows issues airlines have raised and that have been validated by the OEM, and here they are classified by ATA chapter. Notice the amount of complaints fluctuates with and matches the air travel trends. In addition to that, we also have a 3D issue widget with some issues reported directly against the 3D geometry. Here, for instance, cracks have been identified on some structural parts, and we have already started addressing the related issues by using a numerical simulation. Each issue is very tightly connected to the 3D models and aggregates all the information of the resolution workflow. Let's now go to the Service Engineering tab. We can easily see that the Service Engineering department has full access to the engineering definition of the product, the EBOM. The service engineer can navigate through it, and using the full model-based engineering definition of the product, they can define the Service Bill of Materials, SBOM. Here, we are highlighting the consumption and the assignment status from the EBOM to the SBOM. It shows which elements of the EBOM have already been consumed into the SBOM with an intuitive color code. So now we're going to bring up the PPR spreadsheet editor, which presents the EBOM, the SBOM, and the maintenance tasks in a tabular view. Notice that the SBOM items, which are linked to the EBOM, have service-specific attributes that are the responsibility of the service engineering team. If we go through the maintenance tasks, several of them have been defined to cover the main aspects of the flap assembly inspection. We take, for example, the first operation that has been defined, and we go check the work instructions that it has. After reviewing the product in 3D, we activate the different views for the maintenance instruction. Here, we can see an exploded view of the flap assembly, as well as some extra views defined for the other inspection procedures. Notice that the other operations have also a main view. These are all inspection operations. After reviewing the different operations and the views that they contain, we decide to go forward with the work plan publication. We publish the work instructions as they are going to be viewed by maintenance operators using Delmia Appraisal. Now, we go back again into the dashboard to the MRO Execution tab. We can see the virtual twin of the MRO hangar with our aircraft inside. After searching for the maintenance work instructions in the 3D Workbook widget, we have access yet again to the 3D model of the flap assembly, along with the work instructions that were defined earlier by service engineering. We have a view of both the 3D model and the 3D work instructions. They are accessible on any web browser through a 3D dashboard with the 3D Workbook application. Let's now go through the last part of the demo, the maintenance analytics. We start by playing the role of a contract manager who notices that there has been a high number of line maintenance interventions of high severity over the past few months. He therefore decides to assign someone to perform an investigation of this issue, particularly because these interventions have become rather frequent, much more than the predictive analyses of maintenance made them originally think. After receiving the collaborative task requesting an analysis to be performed, the technical specialist goes to the maintenance analysis widget and starts performing the investigation. There is a very strong associativity between the issues that have been raised and the 3D design, as we can see in the screen. There is also a large amount of information coming from documents or older sources that has been aggregated by Exalead. To continue, the technical specialist starts his investigation by taking a look at the remove or replace operations involving this particular temperature sensor and the whole fleet. He cross-checks the data with data coming from sensors or flight data, and he has come to understand the root cause of this frequent issue. After completing his investigation, he saves a report that he can share in the collaborative tasks explaining his findings. We finish by going a little bit more into the predictive maintenance analytics, where we see the machine learning models that have been built to predict the number of failures and the time when maintenance is going to be needed. These machine learning modules are enriched using the big data capabilities that the 3D Experience platform offers.